right, welcome back. We're going to start the second part of this session with a talk on Weyl-Kondo Semimetals from Dr. Qimiao Si.
All right. I guess I should start. Good. So, so this is sort of continuing along the dimension of topological semi-metals, but building the interactions and in the plans that for the first, for part one, we could sort of focus on the aspect where we would mostly stick to the description of fermi-liquid theory, so interactions, the effect of interactions would be such that the system at the end of the day is still adiabatically connected to the non-interacting case. But even here, I'll make some points that interactions nonetheless could cause some qualitative differences. And then the plan for the part two is to go beyond that and see what interactions can do that lead to states, in this case, topological states that are not adiabatically connected to the non-interacting case. So along the way, the parallel of this issue will also be addressed in the canonical correlation physics, because there are some, in many ways, connections between the two sides, which I will explain. So, good. So the, I think it's not forwarding, but it was. So, let's see. Okay. Try one more time. Okay, good. Right. So before I get started, I do want to acknowledge collaborators. A number of the collaborators from Rice in the audience. We've collaborated with a number and continue to do so with a number of formal graduate students and the postdocs, and in particular, I want to highlight the contribution of Sarah Greffy, who's now on the faculty at Cal State Long Beach, and we've had a number of theory collaborators as well as experimental collaborators, and their contributions will come along the way. So, so correlated electronic topology for insulators is fairly well established. The integer quantum Hall effect can be understood based on the band structure, and if you get to the fractional quantum Hall effect, interactions play a zero sort of role, and these are the kind of questions that continue to be of current interest, extensive current interest. For instance, the latest version of this for fractional churn insulators and related states are very much the current ongoing topic of research. In these two lectures, I'm going to cover the gapless case. And so we already heard a very nice introduction earlier this morning about what would happen in particular cases where symmetry prevents the gap from opening, and you end up with a metallic state. That topologically non-trivial, and we heard Suyang's talk about one example of tantalum arsenide being seen from APES and other methods for the the nodes, the Weyl nodes in the bulk, and excitations, corresponding excitations on the surface. So the question that one can ask is whether there's a metallic analog to what happens going from integer quantum Hall effect to fractional quantum Hall effect. Are there good strong interactions drive gapless electronic topological states? So that's the overarching question. This is not the only context where interaction and topology interplay can be asked or is being asked, but it's one overarching theme by itself. So these are gapless electronic states, and the question of the effect of correlation very much connects with the question of electron correlations in gapless, in metallic systems in general. So let me just start by introducing the effect of interactions in general. So we can start from the non-interacting problem in a lattice system with a band dispersion of E versus K, and we have a Fermi surface defined within the Brillouin zone, and then we can introduce some genetic full fermion interactions, Coulomb interactions, and without too much loss of generality, let's consider local interactions. We can generalize appropriately if one would like to. And so the standard way of treating the effect of interactions is to start from the non-interacting limit and switch on the interaction and treat this effect of interaction order by order. And so if in the genetic case, in dimensions higher than 1 with a well-defined Fermi surface, if one does that, one finds that the quasi-particles are very resilient. So what are quasi-particles? If we don't have electrons, we have a Fermi surface, and the low energy excitations of this fixed number of particle system are given by a bunch of particle hole excitation, creating a bunch of electrons and creating equal number of holes. And these many-body excited states can be expressed in terms of elemental excitations, which is nothing else but bare electron or bare hole. In the interacting case, the statement is that if there are quasi-particles, the bare electron can be expressed as a fraction of a well-defined object we call the quasi-particles plus additional pieces. So if you want to deal with interacting systems, the formal way to do that would be in terms of the Green's functions and other propagators. So it says that a single electron Green's function is the sum of a pole with residue Z and plus the rest. And so the pole part, we're going to call it traditionally coherent part, and the incoherent part, the rest is the incoherent part. And this pole is describing the quasi-particle, and that's adiabatically connected to a non-interacting electron if you switch off the interaction gradually. Yes, please.
I'm sorry, maybe you explained, I didn't realize. So the C dagger C for KNP prime is the number operator for electron and hole, right? What's the role of U?
What's the role of what?
U.
U. Yeah, so maybe let me go through again. So this part is just the second quantized way of saying that I have a band with dispersion E and K. Okay? I can generalize multiple bands, but let's not worry too much about that. U is just the second quantized way of saying I have E square over R interaction between electrons. Electrons are charged particles. So if you don't really need second quantization, just for convenience, easier to write. Is that okay? Any other questions, comments? Good. So, so the important part is that we have an object which, if we switch off the interaction, it becomes bare electron. The weight, Z, if we switch off the interaction, would have become 1, but in the interacting case, Z would be less than 1. And this incoherent part is also very important. It captures the effect of interaction. It captures, it reflects multi-particle excitations in a way that the Fermi liquid theory has a very precise way of handling it. I thought it was. Maybe I switched off. Sure. Hello. Want me to use this one? Yeah. Okay. Is this better? Okay. Okay, sorry about that. I think my laser pointer is kind of fading away, but okay, good. That's the best I can do. But there's a water identity and all these ways that we can handle the effect of the interactions. So that makes the quasi-particle picture to be well defined. Now, if one doesn't want to deal with the Green's functions, one could see this quasi-particle in the spectral function that one would measure in the angle resolved photoemission, and you're going to see what this quasi-particle part will be manifested is a sharp peak, sharp in the sense that the width of this peak is smaller than the energy of the center with respect to the Fermi energy, right? So that's an operational definition of a well-defined quasi-particle. And later on, we'll see that the Fermi statistics makes this width to be quadratic in frequency or energy and quadratic in temperature. So that will be a signature that will be becoming very important when we study correlation physics. Good. So, so formally, this perturbation theory in interaction, you can do that to infinite orders, and the quasi-particle weight Z is still non-zero. So these are very resilient quasi-particles to infinite order in perturbation theory. In that sense, the Fermi liquid description is robust. So in that sense, if one wants to deal with interacting systems with interaction that have an underlying well-defined Fermi surface in dimensions higher than 1, one could just say the end result is a Fermi liquid. It's adiabatically connected to the non-interacting case. Now, as it turns out, there are by now a slew of correlated materials in which apparently the Fermi liquid description or the quasi-particle description breaks down. So one has to go beyond the treatment of polar interactions U order by order in perturbation theory. One has to find a way of dealing with effective interactions non-perturbatively. And so one way that has been very productive is to, instead of thinking about the U=0 problem as a reference problem, it's almost like a coupled harmonic oscillators. Instead of thinking about harmonic oscillators as a starting point, you use the interactions to build up some effective degrees freedoms for the low energy physics. And as it turned out, what one can do, going beyond using the bare electrons and maybe also phonons as the ingredients for low energy physics, is that one could use spins and orbitals, which develop when interaction is very large, when electrons become localized or on some large extended energy range, and something that can be formalized in the notion of multi-insulators, where we know electron interaction can localize electrons, and if the electrons are localized, they don't move around, spins can still act as the degree of freedom that could be coupled effectively with other degree of freedoms and create low energy physics. And so put things genetically, in insulating settings, without worrying about topology, correlation is well known to produce states that are not adiabatically connected to the non-interacting limit. A good example of that is multi-insulators. If I have this E of K, this band, if that band is half filled, on average, there's one electron per lattice site in real space. And if E square of R is very large, the electrons don't want to move around, and they end up being localized. So that's something that has been known for a long time in the field of many-body physics. Now, correlated metals, we want to ask questions like whether we can go beyond the Fermi liquid description, whether we can end up with states that are not adiabatically connected with a non-interacting limit. So this becomes a more challenging problem and a richer problem in many ways compared to the insulating case. So I'm going to cover two such examples where one is that it's still a Fermi liquid, but the quasi-particle weight Z is so small that interaction produces qualitatively new effect. And the cases I'm going to consider, the quasi-particle weight Z is non-zero, but could be as small as 10 to minus 3. And so for lack of better term, we're going to call these quasi-particles as fragile quasi-particles, the Fermi liquid as extreme Fermi liquid, just to distinguish from the perturbative regime of the effect of interactions. And then we also want to consider the case where the quasi-particle weight Z has been driven to 0. The quasi-particles are lost, but there could be still some, it's still a gapless system. So that's the coverage. There's many of the questions that are being addressed in the correlated electron systems for this type of ground state and excitations come from the interplay with experiments and the materials platforms. There's a wide range of this, and going from the bulk materials, from the famous one to not so famous one, not as famous one, to low dimensional materials to structures like a Mori system. So I'm going to present, give the perspective from the vantage point of heavy fermion systems. Yeah, please.
So the loss of quasi-particles, what are the consequences of that thing? Like, what is the physical implication of that?
What happens when the quasi-particles are lost? Yeah, maybe we can defer this question. I'm going to come back extensively to that, about that question. Yeah. So the reason is part materials-wise. There's been long history and a large class of large material space for these systems, and quite a few of them are very clean, for example, but also partly theoretical. These are systems you can think of a multi-orbital system. Electrons associated with some orbitals move very slowly because the interaction is very large, while electrons of the other species of electrons are acting more like weakly correlated electrons, with, so therefore they move very fast. So there's some ratios of velocity which is useful as a small parameter. And since we want to do treat the problem non-perturbatively, any small parameter helps with the theoretical progress. So that's the motivation. So here's the outline for part one, which is I'm going to describe in this kind of systems the effect that plays a very important role is the Kondo effect, describing from correlation to topology, I'm going to describe these fragile quasi-particles that I promised to describe. I will apply using these fragile quasi-particles to construct the Weyl-Kondo semimetals. I'll explain what that is. And also to extend to the design of materials in such Weyl-Kondo semimetals. And now, as I promised, so this part still uses quasi-particles. They are very fragile, but the quasi-particle weight Z is still non-zero. But now we want to move on to the case when the quasi-particles are lost. So I'm going to go back to the correlation physics of the study of lost quasi-particles, including some consequences such as strange metallicity. So in part one, I'll just mention that such systems exist. And in part two, I'll come back to describe this correlation physics for the loss of quasi-particles and strange metallicities in a little bit of detail. And then to make the case that there are electronic topological states that go beyond the quasi-particle description. And in the end, I'll just very touch upon some, in a way, just an outlook of some implications of this kind of physics in the context of flat band systems, where there's not, at the atomic level, the separation of scales, velocity scales, for example, but there's an emerging velocity scales which act in a way that's likely heavy fermion cases with a twist. Good. So let's start from the fragile quasi-particles. This is the context of extreme Fermi liquid. As I mentioned, we want to use these effective degree freedoms as the building blocks for low energy physics. One could use orbitals, or more often it's spins. And so these spins arises because that the Coulomb interaction U reaches or exceeds the kinetic energy, the bandwidth. So in that case, spins are part of the building blocks for low energy physics. So the canonical case is for this type of problem. You could consider this to be happening in a variety of materials in this U reaching the bandwidth regime or even exceeding that. They come under the general rubric of bad metals. And in a way, when we come back to the flat band systems, we'll return to that. But in the extreme case is when we have these Kondo lattice systems. So what are Kondo lattice systems? The Hamiltonian is as follows. You have a species of spins, just quantum mechanical spins, and they are defined on a lattice. You have a band of conduction electrons. So there was a question of what the notations are for the EK and U. So this is just the EK term written in real space. It's just the Fourier transform back to real space. So this is if you've taken introductory solid state, this is the tight binding description of the band. And because Coulomb interaction lives in real space, it's good to build intuitions to think about such problems in real space, which now if I have two species of electrons, one of them acts as quantum mechanical spins, the other acts as conduction electrons. In the simplest of cases, I can build the spins of these itinerant electrons and spins of these local moments, and symmetry dictates that they would be coupled by, at least by such exchange interaction. There could be other more complicated interactions, but this is the minimal interaction there would be. So there are other terms in the Hamiltonian that one can build in, but these are the most essential ones. And so for good reason, this coupling is anti-ferromagnetic meaning that it favors the local moment spin and the conduction electron spins to be anti-ferromagnetically correlated. That kind of correlation pays energetically, and then this exchanging interaction between the spins could be ferromagnetic, could be anti-ferromagnetic. Again, typically in the kind of systems we encounter, this is anti-ferromagnetic. And now one should keep in mind that these spins are the spins of electrons, so you can consider this as a model, but it's also good to keep in mind that these spins are nothing else but the original F electrons, which has its own dispersion E of K, has own Coriolis interaction U, and just that because of the F orbitals are very, they are hiding behind some, inside some extended orbital screening is small, effective E square of R is larger than, and the hopping is weak, so the Coriolis interaction is large compared to the bandwidth. So you can consider these as the F electrons, which ends up with being multilocalized. And if they are multilocalized, they would be spins. And they, at this point, yes, please. The subscript? Yeah. The I and sigma? No, the C is the subscript. Oh, yeah. So I'm not, maybe just 30 seconds. Yeah. So I just want to finish the physics or chemistry part of it. So you can say, wait a second. I've learned that there are 7 F orbitals. There are 14 states to worry about. Why are you only consider a spin 1/2 degrees freedom? So that part is actually very important for these materials. You're placing the F orbitals in a crystal environment, which splits the 14 orbitals into bunches. And in a typical environment, it turns out that it's a Kramer's doublet, which lies within the lowest energy sector. So one doesn't want to think about levels which are high compared to the energy scales that you deal with. And so that doublet acts, is our spin. There are cases where the crystalline symmetry, and we can arrange it, and I'll come back to it, is such that the lowest level would not be a Kramer's doublet, but it could be a quartet, or could it be a non-Kramer's doublet. So that's the kind of the things that one can take. Chemistry can be used for engineering these Hamiltonians for the low energy physics, right? So that's, this perspective allows one to consider variations of such models for if there's a particular reason to do so. And as it turns out, that's also a bit, if you want to do ab initio calculations, these kind of considerations make it very hard. And I think from Jay Shinzu's lectures, we're going to learn some aspect of that. So for now, let's consider this as just quantum mechanism glued together with eternal electron physics, with 2 competing energy scales. One is the interaction between the quantum mechanical spins, and there's a number of sources for this exchanging interaction. For simplicity, I'm just going to call this as RKKY interaction. That's what's done in the field. And then there's this interaction, anti-ferromagnetic interaction between the 2 species of spins, which we are going to call Kondo interaction, in tribute to John Kondo, who figured out a lot of physics associated with this. So what is a Kondo effect? Kondo effect, just to say that, let's assume this term dominates. So if this is an anti-ferromagnetic interaction, it favors a ground state in which the localized spin and the conduction electron spin heuristically will form a singlet, up, down, minus, down, up. state. And in reality, we have a lot of sites, so it will be some generalization of this. I'm not going to write down a wave function, but this picture describes the lattice version of that, where you have stack of localized things, the quantum magnetism of it. You have these mobile electrons, which are these waves, and this small arrow represents, and they form a singlet. And that's a very important part of the starting point, because we learned in textbooks that there are concepts such as single mode excitation. Yeah, please.
A quick question. Should I think of those things as effects, or should I think of as volume on every single effect?
Yeah, so the Hamiltonian says that there's one spin at every site, and these sites are coming from the lattice. So there's a translational symmetry, and that's a very important point. Yeah, good. So now, if you have a Kondo singlet, this wave function here, this wave function here can be pictorially represented by having the spin of this local moment and spin of conduction electrons. Spins of itinerant electrons is like exciton. I create an electron and a hole in the spin triplet channel, right? So I have an electron hole in spin triplet channel forming a singlet with the spin of a conduction electron. That's like a bound state. That's like a three-particle bound state. And using concepts like how do we create a roton out of some pictures in Feynman's head about helium-4, for example, you can consider the excitations from starting from this ground state by breaking apart such bound state. So you can kick out a bare electron out, so that's a bare electron state in the excitation spectrum, or you can consider this combination, which turns out to form spin 1/2 and charge E object, and that's excitation that's enabled by the formation of the Kondo singlet in the ground state, and this is the composite heavy fermion. So this object keeps track of the spins, and one could visualize that each spin. So there was a question of whether spins are impurities or spins are associated with a lattice. Spins are associated with a lattice. In the simplest case, there's one per site. So each spin is going to generate one electron excitation. Okay? And these are, it's very sluggish. It has a hard time to move around, which is why in the end, you have these quasi-particles, but they are very heavy. The velocity is extremely small. And so this qualitative physical picture can be converted, can be captured by a calculational scheme, which becomes exact in some large N limit. I'm not going to describe the large N limit. So in a precise way, one can treat order by order, but now I'm no longer doing perturbation theory in U. The zeroth order is the saddle point limit of this Hamiltonian. So you have E of K, which is the Fourier transform of Tij. That's this dashed line. That's the band of conduction electrons that where you started with. And the composite heavy fermions essentially is a flat band. It's a very weakly dispersing, and this flat band hybridizes with the band of conduction electrons to form these renormalized bands at the saddle point level. And these are sharp quasi-particles. The weight is the energy scale, that's a Kondo scale, divided by the bare conduction electron energy scales. So the Kondo scale turns out typically to be on the order of several milli-electron volts. The bare electron energy scale is several electron volts. So the ratio is about 10 to minus 3. And so this Z being 10 to minus 3 shows up as is manifesting in a number of ways in the flatness of the states, single electron excitations near the Fermi energy, and also in a gigantic quasi-particle peak in the quasi-particle denser states. So these are canonical descriptions that you would encounter as the cartoons for heavy fermion states. But we should recognize these are just ferromiliquid. It's adiabatically connected to some non-interacting limit. It's extreme case. Yes, please. Yeah, so going back, so there's one has to different, this question, it's a good question. It needs to be asked in two separate ways. One is about the ground state, one is about the excitations. In the ground state, the spin is bound, as I said earlier, particle-Hall combination in the triplet channel. So that's the spin singlet. Okay, up, down, down, up combination. Now, once I have a ground state, I can ask your very same question about excitations. And excitations, as I said, you can kick out objects from the bound states. You have the bare electron, which in the end is represented by this dashed line in the energy dispersion, and this heavy object, which is a composite object. Okay. So, yeah, so that you have to get used to a dispersion like this. But if you put chemical potential, you have to convert into particle and Hall language. Okay. So particle is, as usual, just creating a electron above the Fermi energy. Hall is just removing electron from the occupied part. Okay. Is that okay? Okay, very good. So, there's one more feature associated with in this caricature, namely these peaks captured in the composite fermions, they are bound to the Fermi energy, because in the fermionic sector, when we say we have created low energy excitations, it means that it's bound, it's pinned to the immediate vicinity of the Fermi energy. And that's a feature that we're going to utilize in considering the Weyl-Kondo semi-metal. So to summarize, this is a case where we have extreme fermi-liquid. Z, the quasi-particle weight is non-zero, but very small, on the order of 10 to minus 3. And it could set the stage to violate this dictation of perturbation theory to infinite orders that quasi-particles must exist. If Z is already that small, competing interactions such as RKKY interaction might be able to destroy it completely. So we'll come back to that issue. For now, let's stay in the regime where the Kondo physics dominates compared to the quantum mechanism, and we have non-zero Z, and let's ask, what can we utilize that? And so that leads to the Weyl-Kondo semi-metal. The reason we came to it was not as direct as I described. We were thinking about some phase diagrams for the breakdown of Fermi liquid, which I'll come back to. So this, for now, just consider this as a cartoon. And there's multiple phases in this zero temperature phase diagram. And we were asking ourselves in a phase diagram like this, how can we go from one part to the other part? And we had with silk compulsion, we had some idea of using spin orbit coupling as a tuning parameter. And that led to a question, well, what if you include spin orbit coupling, could that actually modify this phase diagram? So that was how we came to the Weyl-Kondo semi-metals. So the first question that can be asked is, in a way, a very modest one. Is there a Kondo lattice model whose ground state or Anderson lattice model, which I have not described, but just one step back in hierarchy of energies, that the ground state is topologically trivial without the Kondo effect, but becomes topologically non-trivial with Kondo effect. So with that motivation, this was Sarah Griffith's thesis work. We came to the three-dimensional analog of what Su-Yang talked about. The graphene is a case where you have a symmetry-protected Dirac nodes. The three-dimensional analog would be the diamond lattice, where you have A and B, just like a graphene case sublattices. There's the inversion symmetry, where the inversion center is sitting at the middle of the bond that connects nearest neighbor pairs of sites from A and B sublattice. And if we know what the inversion center is, we can break the inversion symmetry by introducing potential that differentiates between A and B sublattices. And so this model, just for definiteness, we consider quarter filling. So you have 2 sites per unit cell, 2 orbitals per site. And if I have 1 electron per site, by the counting, it's a quarter filling case. And so consider the case that genetically these F orbitals, Kondo lattice or Anderson lattice defined on such a lattice. The levels of the F, as I already explained, these are inner orbitals. They're hiding behind the extended orbitals. So their energy is lower compared to conduction electrons. So if I have 1 electron per site, genetically that electron wants to go to the F orbital. And so then there's nothing left for the conduction electrons if there's no coupling between the two. And this represents half filling of this Kramer's doublet of the F orbitals, and the interaction is large. They form a Mott insulator. So we end up with, from single electron perspective, at low energies, there's no spectral weight at all, nothing. There's basically, in the end, some spins, which are decoupled from conduction electrons. And these conduction electrons could, and they do, have symmetry protected nodes, degeneracies in the band structure, but they're genetically very far away from the Fermi energy. So unless you do what Suyan described, just with particular materials design, genetically anything like nodes would be sitting very far away from the Fermi energy. Good. So now, on the other hand, if I turn on the Kondo effect, I promised that the Kondo effect is going to produce heavy, composite heavy fermions, and within the saddle point description, they would form bands. They are very heavy bands, and they are pinged to be very close to the Fermi energy. They must be. They have no choice. And so now, if you look at the quarter filling case, if you count the number of electrons, the natural choice would be the system to be a semiconductor, and so would it be gapped there will be no states at Fermi energy. This would be a Kondo insulator, and the Kondo insulator as a materials class does exist. Yes.
Stupid question. Does it depend on the assumption that the F electron is at the Fermi energy to start?
F electrons are away from Fermi energy. So if Fermi energy is here, so I might have bands around here, conduction electron bands. The F electron would be sitting sufficiently below the Fermi energy, not miles away, but sufficiently below it. And so that's why they become localized and they become Mott insulator. It's the formation of the Kondo singlet that creates these composite fermion excitations, and these excitations have the energy spread of kBTK, which is 3 orders of magnitude smaller than the usual the bare bandwidth, and they are pinged to the Fermi energy. They don't have a choice, because these are low energy excitations. Okay. So I want to make a point that they are pinged near the Fermi energy. In this model, you would have the Kondo insulator, but because it's a diamond lattice or small weak perturbation away from the diamond lattice, symmetry prevents the Kondo insulator gap from forming. And in fact, you have these nodes, and there's almost emerging particle Hall symmetry, so the nodes have no choice but to be in the middle of the gap, and the most natural choice to be exactly at the Fermi energy, at least in this model. Genetic models would be somewhat away from the Fermi energy, but still in the immediate vicinity of the Fermi energy. So that's important because So in the model, we define Weyl nodes, and because these are Weyl nodes associated with Kondo-driven excitations, they are pinged to the immediate vicinity of Fermi energy, and also the velocity is extremely small, 3 orders of magnitude smaller than the graphene electron velocity. So the velocity would be on the order of velocity of sound. Yeah, please.
Can you elaborate on why, like, including this Kondo effect will lead to some emergent, like, particle-fold symmetry?
Yes. So as I said, the Kondo singlet, you should picture that as a ground state. So imagine you have a superconductor as a ground state. You have Cooper pairs, that's a bound state, right? So how do I understand the excitations, which would be the group of de Gennes quasi-particles? You just break apart the pairs. That's how you create the excitations. It's the same story here. If I have a bound state in a ground state, I break apart, and this big fat object that's a composite, that is the composite fermion. Okay. Is that okay?
Yeah.
Okay. Good. So now these turns out to have consequences. The small velocity is reduced by 3 orders of magnitude. Something bad happens. You cannot see it in APAS spectrum, unfortunately. The energy resolution hasn't reached that yet. But something good happens. That's what the colloid electron community does, which is to look at the entropy. And if velocity is reduced by 3 orders of magnitude, you have a node sitting at the Fermi energy. The specific heat would be T cubed with a prefactor that's amplified, enlarged by 9 orders of magnitude. So that's, it turns out, at the same time, our collaborators in Vienna had a new Kondo semi-metal that shows precisely this specific heat form of specific heat with the prefactor, the slope of T cubed difference, that's almost 9 orders of magnitude larger than what one would have expected if you have nodes in 9-12 electrons. And moreover, if the nodes are pinged near the Fermi energy, you could have slight deviation of filling so that the Fermi pocket, the Fermi surface would be very small and centered around the Weyl nodes. So that means that on the Fermi surface, the Berry curvature will be extremely large. It was explained earlier this morning that at a Weyl point, the Berry curvature diverges. So if you have a tiny pocket, Berry curvature on the Fermi surface will be extremely large. As it turned out, that becomes manifested in some Hall effect, which I will not explain. It's the nonlinear Hall effect in extreme. The tangent of Hall angle is almost half. That's a gigantic number. So I think let me just spend a couple of minutes utilizing this construction to design Weyl-Kondo semimetals. And so the notion is that I think I pretty much said enough of it, namely using strong correlations, in this case the Kondo effect, to produce low energy excitations. And these low energy excitations, they live in the same lattice, so they must be constrained by the lattice symmetry among other symmetries. And that turns out to be a way to, at least it's a possible way to think about looking for materials. And for generality, we went beyond the diamond lattice, in this case, some square nets with these particular space groups to show that the Kondo effect could also generate other type of nodes, such as the nodal line, the line nodes that was also mentioned earlier in the morning, but again associated with these composite fermions, and you can calculate a variety of things to show that that is a topological nodal line semi-metal. And in addition, because the Kondo, it's a interaction-driven effect, it's a robust effect. I don't really need to fine-tune the filling all that much. So we can that allows us to follow to have the following prescription. Let's go to database to search for particular space group materials that has, say, as an example, cerium atoms sitting at some particular positions of the crystal lattice. So the database spits out certain number of systems in it's an interacting system, so we have to use some screening process to see that these are to focus on candidate materials that are semi-metals, not good insulators, not good metals, not good superconductors. Yeah, there's a question. We just want to start with an example, and what cerium is a canonical heavy element for creating heavy fermion compounds. Why not? That was really the motivation. Yeah. So then one has to do the database doesn't have information about whether the system actually is correlated or not. So we use the entropy criteria to see that it's correlated. The database doesn't really say it's a semi-metal or not. You look at the transport or quantum oscillations, carrier concentration, etc. And we did also some DFT just to serve as a sanity check about symmetry constraints. So that led to, as an illustration in these two space groups, in this very particular choice of cerium at some particular sites, led to three materials. One of them, our collaborators actually made and measured the specific heat and has the temperature dependence associated with the nodal line semi-metal. And so that's pretty much what I want to say today. Just as a prelude of what I want to describe in the next lecture, coming back to this motivation that I already said earlier. And could strong correlation drive gapless electronic topological states that are not adiabatically connected to the non-interacting limit? And we're going to use the strange metal physics. Strange metal physics is a very hard piece of physics to crack, but we have enough intuition to utilize that, to do something for us. And we're going to use the loss of quasi-particles, which I'll explain in the next lecture, to our advantage to create a topological states that are not adiabatically connected to the non-interacting limit. And so as a prelude, these are the kind of charts that you look at in the correlated electron community to say that, hey, the color, and I'll explain tomorrow, that the color tells us that the quasi-particles may be lost. And then one could actually do a bit more to prove that the quasi-particles are lost. And we are going to use that intuition to search for topological states that go beyond the quasi-particle description. So thank you very much.
I know you didn't go into like very fine detail about your like Weyl-Kondo Semimetals model, but I guess there will be some like 4 fermion terms in that model, right?
In the model that I already described?
Yes, I mean in your so your Weyl-Kondo Semimetals model is like a Kondo lattice.
Yeah.
Kondo like Hamiltonian on a non-centrosymmetric lattice, right?
Yeah.
And in there will be some covered term or something.
Yeah. So
my question is just in one slide you showed that you calculated the Berry curvature. So how do you define the Berry curvature if you have an interacting model?
Yeah, that's a good question. Yeah. So maybe there are two aspects to it. Okay. What is a model? So I've written down a spin form, the Kondo lattice form, but the parent form of this is instead of the spins, it's just bare electron, using electron as the building block, except that there's a gigantic U associated with that species of electrons. And so that's called the Anderson lattice model, as opposed to be Kondo lattice model. But in a large U limit, it reduces to the Kondo lattice model. Now, the second part let's see, maybe you can remind me about the second part of the question.
It's about the, so when you go to calculate the Berry curvature,
Yeah.
you have an interacting model,
Yeah,
so I'm wondering how do you define
Yeah, so as I said, in a saddle point treatment, I end up with renormalized bands. There's no lifetime. Lifetime is infinite, and it's sharp excitations. That was how this calculation is done. If you go beyond saddle point level, there will be finite, this quasi-particle peak, I showed you, it's not going to be a delta function. There's going to be a finite width. And so then this approach doesn't work anymore. And it turns out that we can generalize this by using Green's function. So instead of using block, if I have renormalized bands, I still have effective block states. But if I want to treat the damping and then, for example, going to the non-Fermi liquid case, I have to. Then it turns out you can use some eigenfunctions of Green's functions to replace block functions. And then you can still construct a Berry curvature, etc. So I'll mention briefly tomorrow.
Yeah, thank you.
So on the slide where you show the band structure, the positive electrons, why isn't it exact particles?
Why is it not? Oh, because my model does not have exact particle Hall symmetry. So we study quarter filling, and so I have, more bands which are left empty compared to the bands which are occupied. Right? If I were half filling, I may be able to engineer the Hamiltonian to have particle symmetry, but quarter filling inherently is a problem that does not have particle symmetry. But because if I restrict to low energies, which is just the heavy bands, then I don't worry about the high energy states, and effectively it's like half filling of the low energy sector. That's where the effective particle Hall symmetry arises.
Does the non-trivial Kondo require to have it when you're in Kondo?
Correct. Yeah, so if the Kondo coupling, if a spin coupled ferromagnetically to the spins of a conduction electron, that's a well-defined problem. That coupling effectively at low energy goes to zero, renormalized to zero. So if you quantitatively, you can think that a singlet, in that case, would it be triplet? And triplet is very different from singlet. It's not an entangled state.
Is there anything unusual about the Kondo breakdown?
Yeah, so the loss of quasi-particles that I will describe, I assume there's a question about a bulk. Yeah, the loss of quasi-particles precisely come from getting back the dynamics of the RKKY interactions, and that competes with Kondo singlet formation. And this competition leads to, say, magnetic ordered phase or spin liquid phases, and the transition point is where the quasi-particles are lost. So maybe tomorrow